In today's video, we're going to explore how atoms form covalent bonds by sharing electrons, and we'll also look at the different ways to represent these bonds visually. But before diving into covalent bonding, let's quickly revisit what we already learned about ionic bonds, where atoms transfer electrons from one to another, creating oppositely charged ions that are then held together by strong electrostatic forces. This transfer happens because each atom wants a full outer shell of electrons, and this works perfectly in cases like sodium and chlorine, where one atom has an extra electron and the other is missing one. However, when we deal with two nonmetal atoms, like two chlorine atoms, the scenario changes. Both of them need one extra electron to achieve stability, so transferring electrons doesn't help either of them. Instead, they choose to share electrons. In this case, each chlorine atom shares one of its electrons so that a pair of electrons is shared between them, effectively allowing each atom to feel like it has a full outer shell. This sharing of electrons is what we call a covalent bond, and we can represent it using a diagram known as a dot and cross diagram, where the electrons from one atom are shown as dots and those from the other as crosses, allowing us to distinguish which atom contributed which electrons. While these diagrams usually only show the outermost electron shells, sometimes you might be required to draw all the shells depending on the exam question, so always check what's being asked. A quicker and more practical way of drawing covalent molecules is using the displayed formula, where we write the chemical symbols and use lines to show bonds between atoms, each line representing a shared pair of electrons or a single covalent bond. These diagrams are especially useful for large molecules which would be too complex to draw using full dot and cross methods. For example, a molecule like glucose, although you don't need to memorize its structure, can be shown using a displayed formula, and it's important to recognize this type of representation. The limitation of displayed formulas, however, is that they don't show the three-dimensional shape of molecules. To address that, we use 3D models, which attempt to show the actual spatial arrangement of atoms in real life. For a slightly more advanced example, let's look at how covalent bonding works in ammonia, with the chemical formula NH. From this formula, we know there's one nitrogen atom and three hydrogen atoms. We start by drawing their outermost shells. Hydrogen, which is in its first energy level, can only hold 2 electrons, meaning each hydrogen atom needs one extra electron to complete its shell. Nitrogen, on the other hand, is in its second energy level and requires 3 more electrons to complete its shell of 8. Therefore, if each hydrogen atom shares 1 electron with nitrogen, and nitrogen shares 1 electron with each hydrogen in return, all the atoms will end up with full outer shells. This gives us the correct dot and cross diagram for ammonia. If we wanted to show this as a displayed formula instead, we would erase all the shells and electrons and simply draw lines representing the shared electron pairs, with each line indicating a covalent bond. Now, when trying to represent ammonia using a 3D model, things get a little more complex because predicting the exact shape of molecules in 3 dimensions can be tricky. Fortunately, at this level, you don't need to know the exact geometry, you just need to recognize what a 3D molecular model looks like. The final thing to understand is the different types of substances that covalent bonds can create. So far, we've seen simple molecular substances like chlorine and ammonia, which are made up of small molecules held together internally by strong covalent bonds, but between these molecules, there are only weak intermolecular forces, making them relatively easy to separate. Other common examples of simple molecular substances include water, which is HO, and methane, which is CH. However, covalent bonds can also form much larger and more complex structures such as polymers and giant covalent lattices. Polymers are long chains made from repeating units called monomers, and these are used to manufacture everyday materials like plastic bags and t-shirts. On the other hand, giant covalent structures include substances like silicon dioxide, diamond, and graphite, where billions or even trillions of atoms are bonded together in a continuous network or lattice. These structures are extremely strong because every atom is connected to others by covalent bonds throughout the entire substance. And with that, we've covered the essentials of covalent bonding and the different ways of representing it. If you found this video helpful, make sure to share it with your friends, and we'll see you in the next one.